Now, there's a way you might be able to get around it that I don't know if anybody has ever tried. So I just thought about this when I was preparing for the class. Want h such that h of x equals h of x plus c. We took h equal f plus g, and it didn't work. Take h equal r of f g, r, where r is some nonlinear function, which can be as horrible as you like. Well, now h is no longer a linear combination of f and g, so this trick does not work. So I don't see any way that Alice and Bob can speed up Simon's problem with classical communication if you make R nonlinear. In particular, if you make R a nasty nonlinear function. And they can still do it. I mean, Alice can still produce, Alice can still query Simon's algorithm by message passing with Bob, although it's a little more complicated this time. So let's go over that. Alice sends Bob x b or no. x0. Bob sends back x, g of x. Alice computes. Okay. Keeps b. Alice computes x, g of x, b plus r of f of x, g of x. So Alice has b in this register, and she just computes this horrible nonlinear function f of xg and g of x. So now this is good, except Alice has this extra register g of x that might wreck the coherence of Simon's algorithm. Alice sends x, g of x to Bob. Bob uncomputes g. Sends x0 to Alice. And Alice has x b plus r of f of x, g of x. And this is the Simon oracle that Alice needs to run Simon's algorithm. And we have kept this clever trick from working because it depended on linearity. So is this version of Simon's algorithm, does it really give an exponential speed up in terms of communication complexity? And I don't know how to prove that, but I think it probably does. And I should say that there are other communication complexity problems that do provide an exponential speed up. And I don't think I'll talk about them Thursday. What I think I'm going to talk about Thursday is fingerprinting, which is another kind of distributed quantum computation.